frustrate your existing users. So today, I'm not going to talk about rewriting. Instead, I'm going to talk about porting. And the difference here is a little subtle, but the general idea is that a port should be incremental. You're not really throwing everything out and starting from the beginning. You're aiming to port pieces individually, and you're also not trying to reinvent anything. The goal here is that the product should work exactly as it did before. There should be no breaking changes, nothing. So yeah, this talk is about porting Turborepo to Rust. So let's start with what Turborepo is. Turborepo is a build system for JavaScript. It allows you to scale up your builds, often inside a monorepo. And let's go through this simple example here. Let's say you have two web apps that both use a shared UI library. If you were to build this normally, with something like Yarn Workspaces, it would build everything in serial. You would essentially have to lint everything, then build everything, then test everything. And that takes a while and just doesn't scale up, means your CI is slow, and just means it's a bad user experience. With Turborepo, you can do things in parallel. Turbo is able to determine which tasks can be run in parallel, and it effectively speeds everything up. And at the end, it will cache the outputs. So you can essentially make sure that if you try to run the task again, you'll just read from the cache. You won't try to run the task again. And in fact, this cache can be shared between different users and different computers using Vercel's remote cache. And for the architecture, it's a native binary that's compiled for 6 targets. That's x86 in ARM times Windows, Mac, Linux. I love the little creepy Linux here. My favorite. And it's about 70,000 lines of Go. And that consists of an execution pipeline, a daemon, which helps speed up the process by essentially watching for changed files, another command called Prune, which we'll get to later, and some secondary commands like login and logout. Going through the execution pipeline, it's pretty straightforward. You essentially just load a bunch of config, you spin up the dependency graph of the different packages that depend on each other. And then from there, you spin up a separate graph called the task graph, which is essentially a graph of the different tasks that need to be executed. And so like, for instance, you could have a lint task that a build task depends on, or you could have a build task that depends on the build task of other packages. And from there, we traverse this task graph and execute the different tasks. If we can determine that a task has already been run, then we restore from cache. And at the end, we build a summary of this execution. So why did we decide to port? The first reason really came down to alignment. Now, Go is a really great language. And what it really excels at is building web applications. You can build a web application that is hosted on a server of your choice. And oftentimes, this server will be a Linux server. Therefore, Go tends to assume a Unix world. And this shows up in a few places. One place in particular is with file permissions. In Go, if you want to change the permissions on a file, you can set a Unix-style file permission code. And this works great if you're on a Unix system. But if you're on Windows, it actually doesn't work very well at all, because Windows does not have a commensurate feature such as file permission codes. And so when you set the file permission code, Go will basically just lie to you. It will say, yeah, sure, I've set that code, but it didn't do anything. And it's like subtle differences like this that makes it really tricky to write cross-platform code. One important part of Turborepo is that we're taking files that may have been produced on, say, a Linux machine and restoring them on a Windows machine. And when you have file permissions, well, you need to get them right. Another aspect is really about ecosystem. Turborepo is, by its very nature, a product that uses a lot of file formats. We have to read JSON, YAML, protobuf, and so on. And Rust is really great for that. It has a wonderful library called Seride, which is really great at serializing and deserializing different formats. And also, we have a sibling project called TurboPack, which is our Rust-based successor to Webpack. And so we want to share code between the two. Finally, Rust has become the language of choice for a lot of JavaScript dev tooling. And so there's a lot of amazing projects out there that we can leverage. For instance, Biome is really great if you want to have high quality parsers for JavaScript, JSON, TypeScript, and so on. NAPI is great if you want to interoperate between Rust and JavaScript. And SWC is, of course, an excellent compiler written for JavaScript. And by leveraging these different projects, we can add a lot of features that we couldn't have added in Go. So how did we start the port? Now, you can imagine a scenario where you just start from scratch. You build a command line, then you build a basic package graph, a task graph, and you're like, hey, we're doing pretty good, we're getting somewhere. Except there's a lot of features. Again, 70,000 lines. It's not a trivial project. It's a mature project with a lot of different features used by a lot of different people. And so our goal instead was to not do a rewrite. We wanted to keep our port incremental. We want to keep shipping features to users. And we want to, in fact, start with a new feature. We want to basically allow users to gain something from the new Rust code instead of losing something. Any idea where the music is coming from?
Right in the room next door.
OK. All right. Well, good soundtrack, I guess. Anyways, the way we started is with what we call the Rust shim. And the Rust shim is essentially a Rust-based wrapper around the existing Go code. We would compile the Go code to be a C library and then link it into the Rust. And this would implement a new feature called Global Turbo. And what this feature does is it allows you to use Turborepo as a normal command line utility, but when you run it inside a repository, it will essentially delegate to the local version of Turbo installed in that repository. And so this allows you to essentially pin the version of Turborepo used inside your repository, but also use it as a normal command line utility. The next feature after that we decided to port was CLI parsing. And this was a pretty natural next step because CLI parsing we were already doing a little bit of that for the shim. And so we ported the CLI parser using an excellent library called clap, which allows you to basically define a struct full of your flags, and then clap will create the command line parser for you. And from there, we took those args and we serialized it to JSON, and we sent it to the Go binary. And the reason why we use JSON here is that, again, our interop is using C. And C is not a fun language to write in a cross-platform manner. We didn't really want to have a bunch of C types laying around that we had to worry about. And so by instead passing just one big string, we could avoid having a large surface area for our C API. Now, with these two features, we decided to ship our first Rust code to users. But of course, this didn't go to plan. And so we ran into a few shipping issues. The first came with Windows. Now, if you're familiar, Windows has two different implementations of the C standard library. This is MinGW and MSVC. And they're not really compatible. The issue here is that Go only uses MinGW, and Rust on ARM only uses MSVC. So we couldn't link the two together. And so the solution we came up with was a pretty lame one, but it turns out that Windows ARM has an emulator, so you can run x86 binaries. And so we just shipped x86 binaries for Windows. It would be a little slower, but we decided to live with it for the duration of the port. Next up came Alpine Linux. Show of hands, who here has used Alpine? Ooh, I'm sorry. Anyways, Alpine is a distro of Linux that is especially lightweight. It's often used for Docker containers. And what makes it lightweight in particular is that it doesn't come with an implementation of glibc, which is the standard C library implementation. And this creates a problem when you have most binaries, where most binaries tend to dynamically link glibc. And what that means is the binary essentially calls out to the operating system's version of glibc. If that isn't there, well, the binary won't run. The normal way you solve this is you install a compatibility layer, which essentially installs glibc for you. But in our case, we want to support especially old versions of Alpine Linux. And this made it so we couldn't really use a compatibility layer, because the compatibility layer was too old for the binary that we were building. Instead, we decided to use Muscle, which is an alternate C standard library, which can be statically linked. glibc is often not statically linked due to licensing issues. And this seemed to work pretty well. We could statically link everything, get it to work on Alpine, and ship it. Except we psych faulted almost immediately. Turns out, when you run a binary on Alpine, it would just crash. And when we looked in a debugger, it was coming from the middle of the Go runtime, and the stack was corrupted, and there was really no explanation about what was happening here. Eventually, we found this lovely 9-year-old GitHub issue with like 100 comments that basically explained that you can't build Go as a C library and run it with muscle. It just won't work. It'll crash. And there's no real solution in sight for this. So this was a real problem. We had to support Alpine, and we couldn't figure out any other solution, really. And so we had to go back to the drawing board and basically figure out another approach here. And what we eventually came up with was what we called two binaries, where we built the Rust code and the Go code as two different binaries, and then we essentially had the Rust binary call the Go binary. And because we were using JSON to pass the arguments, this was pretty easy. We could just essentially send the JSON payload as one big command line argument. And so with this, we were able to ship our first bit of Rust code in Turbo 1.7. Next up is what we call the Go sandwich. So at this point, we had ported a few things with the shim. We ported some login, logout commands, and so on, and those are pretty straightforward. But we had to start porting the main execution pipeline. And this was kind of tricky because the main execution pipeline almost immediately spins up a graph of your repository. And graphs are notoriously not very serializable. We didn't really want to pass this through JSON. It would be way too slow and just way too inefficient. And so we tried to come up with a few different ideas here of how to port. One idea was using the daemon, but the daemon is really an optional performance improvement, and so we didn't want to make it mandatory. Another option was what I called a trampoline. So you essentially re-execute the Go binary multiple times to essentially go through the execution pipeline. So you call it once, you get some data back, you call it again, you get some data back. But that seemed a little suspect, and we didn't really want to rely on executing binaries too much. It seemed a little hairy. So what we eventually came up with is what we called the Rust Go Rust sandwich, or the Go sandwich for short. And it's exactly what you think. It's essentially, we ported dependencies inside the Go code to Rust and linked them into the Go binary. And this works because while you can't link Go to Rust, you can apparently link Rust to Go. And these individual dependencies, we would communicate back to the Go code using protobuf. Protobuf was a natural fit here because we were already using it in the daemon, and JSON started to get a little tedious because the interfaces would get out of sync. With protobuf, you can just generate the interfaces from the protobuf spec. And so with that, it created a really nice workflow for porting things. We're able to take a dependency, split it out into a separate Rust and Go version that we could toggle on and off. We would then build this Rust implementation. We would write a bunch of tests. Oftentimes, these tests would actually be in the Go code, because then you could call the Rust code, get the result from Rust, and compare it to the result from Go. And then from there, you would open a pull request and merge it. And with this, we were able to port a few features, like lock file analysis, file hashing, our Git integration, and so on. And now for more shipping issues. Because as you've probably anticipated, shipping a Rust Go Rust behemoth to 6 different targets was kind of an adventure. So again, we're using 6 targets here. And because we're using 6 targets, we have to do a cross-compilation. And what that basically means is you're building for a different target than the machine that is compiling the code. So you could be building on an x86 Linux machine, but targeting a Windows ARM machine. And normally, when you do this in Rust, it's pretty easy. Rust has a great built-in facility for cross-compiling your C libraries, and it all kind of works pretty smoothly. But in this case, the Rust code wasn't actually the final step. Rust was basically just being built as a C library, at which point the Go code would take over and complete the binary. And so Go didn't really have knowledge of the C libraries that Rust was using. And so Go couldn't really cross-compile this very cleanly. So we had to figure out a way to cross-compile our C libraries manually and do it in a way where it didn't, cause a whole bunch of headache. Because if you've ever done a cross-compilation for C code, you know that it's a little tedious sometimes. And if you're wondering, no, we couldn't stop using C. Like C is everywhere. It's even in the Rust runtime itself. So we pretty much had to support C. So how did we do this? Well, in classic Hacker News bait, with another language. We use Zig, because Zig, as it turns out, has a really great cross-compiler for C. It's called ZigCC, and it works beautifully. It allows you to cross-compile to all the targets we wanted. It includes sysroots, which is basically an index of all the different libraries you need. And yeah, it's great. So with that, we're able to get out Turborepo 1.8.6 with the Go sandwich. Finally, let's talk about the run outline. So at this point, we had ported quite a few features with the sandwich. But we started to reach a limitation. And this limitation really came around asynchronous code. You see, with all the other features we'd ported, there wasn't any async there. So the Go code could kind of think of the Rust code as just a straight normal function call. It calls the Rust code, it waits until the Rust code's done, and it returns an answer. But with async code, that doesn't really work. You have to essentially have some way of the Go runtime, which is itself an asynchronous runtime, have it understand, hey, I have to wait for the Rust code to finish. And also, we didn't really want to share these two async runtimes in the same binary. We didn't know what complicated operating system features each runtime was using, and we didn't really want to figure that out. So at this point, we decided to just go all in on what we call a run outline. And this is essentially an all Rust execution pipeline with the unimplemented parts stubbed out. So you'd start with essentially a dummy package graph, a dummy task graph that didn't really do anything, and you would add pieces as we went along. And we added a flag so that you could try out this run outline. Now, you may be wondering at this point, doesn't this sound like a rewrite? And yeah, you'd kind of be right. This is a rewrite. But it's important to remember that at this point, we had had several months of porting and several months of progress under our belt. The sandwich and the shim had bought us a lot of features. And so at this point, we had some pieces to go, but we had managed to get our team ramped up on Rust. We'd managed to implement a lot of features. And so now it was time to go all in on Rust. However, at this point, we did run into a key issue. And that was an issue of unused code. With the shim and the sandwich, it allowed us to exercise the Rust code. We could run it, and users could run it, and we knew that it worked. And really, that's very valuable. You can write all the tests you want, but ultimately, it's no replacement for someone running your code. Users will find all the nitty-gritty issues that you can't even imagine. And so now that we were building this run outline, we had to figure out how can we make sure that this code is being executed so that we could be sure that it actually was working. The first way was with Prune. Prune is a command that allows you to strip down your monorepo into a smaller subset. And this is really valuable if you're running inside a Docker container, because you can essentially strip out all the packages you don't need. So in this case, if you prune to just the A package, it'll keep the A package and all of the A package's dependencies. And this used the package graph. So we could port the package graph to Rust and then implement Prune. And another part of it that Prune uses is the lock file analysis, which we'd already ported via the sandwich. And so it ended up being pretty straightforward to implement this. And it, again, allowed us to make sure that our code worked. Next up was hashing. So hashing is at the core of Turborepo. What hashing does is it allows Turbo to figure out whether a task has been run already. And the way it does this is it takes all of the inputs to a task, whether that's files, environment variables, and so on, and it computes a single hash. From there, that hash is used to index into the cache. And if there's a value inside there, then we know that the task has already been run, and we can restore from the cache. And yes, task, hash, and cache all sound exactly alike. That was extraordinarily confusing during discussing this. So what we decided was that hashing should stay the same between Rust and Go. And this meant that we could use it as a point of comparison. If we did all this work and we got the same exact hash, we could be certain that the code worked as intended. And the way that we did this was by moving to a language-independent hashing algorithm. Specifically, what we did was we decided to serialize both the Go and the Rust values to Captain Proto. If you're not familiar, Captain Proto is an excellent serialization format that is defined byte for byte. And what this allows is for essentially zero-copy serialization. You can serialize to a chunk of memory and then have a different language read from that same chunk of memory. And this is great because, again, it's language agnostic. It's defined literally byte for byte. So we knew that if Go were to serialize to Captain Proto and Rust were to serialize to Captain Proto, we get the same exact values. And so with that, we're able to test our task graph, package graph, and task execution. And we ran this on Alver Tests. So Alver Tests would also check that the hash is matched. At this point, we were in basically a dead sprint to finish the port. So we started porting the package graph, task graph, remote cache, and we just kept on going. And yeah, and so we pretty much finished the rest of the code right here. And at this point, we started to think about how we're going to ship this to users. Because again, while hashing and Prune gave us a pretty reasonable certitude that things would work, we still wanted to be careful. And so we started by first telling people about the Rust flag, and then we started to burn down the broken tests and make sure we got to 0 and made sure that the output matched practically almost byte for byte. And then from there, we dogfooded it internally in Vercel. Vercel has quite a few monorepos that all use Turborepo, so we switched it on to the Rust version. And then from there, once we reached 72 hours of no bugs on Vercel, we shipped the all Rust version with a Go fallback in case you ran into bugs. And so Turbo 1.11 was all Rust. So what did we learn? Well, we had some good successes. The first is that we managed to move 70,000 lines in 15 months. And you may be saying, 15 months, that's a lot of time. And yeah, it is. But there's a big difference between 15 months where you're radio silent, you're not shipping features, your users are wondering what's happening, and 15 months where you're still shipping stuff, you're still fixing, users know what's going on. There's a massive difference there. Another big win is that we didn't get bogged down in second system effect. If you're not familiar with second system effect, it's this idea from Fred Brooks and his work, The Mythical Man Month, that designers, when they tend to build the second version of a system, they take way too long, they go over budget, over schedule, and that's because they try to build the best possible version of the system. They basically think, hey, I've built the first version, now I'm going to do it right. And that is the kiss of death. And so we didn't get bogged down in that. We focused on just getting the job done and shipping. And we also managed to use serialization formats to our advantage. First with JSON in the Rust shim, then with protobuf in the Go sandwich, and finally with Captain Proto. And finally, we managed to get the team ramped up on Rust. And this was a great win because when we came in, we had some team members who knew Rust quite well, myself included, and we had other team members who only knew Go. And so by doing this incrementally, we could have people who are beginners in Rust ramp up starting with small features. If we had done a full rewrite, then those people would have had to just basically learn Rust from the get-go, and there would have been a lot of pressure. By keeping things incremental, they could still work on some Go features and start to add to the Rust code. Of course, there are things that we could have done better. And really, the first one was investing in maintenance. We came into the port with this idea that we could kind of fix things up while porting, and that quickly turned out to not be the case. So this created some issues where we would have to port features that were deprecated, but we knew that we couldn't eliminate it in the middle of the port. we wanted to be able to roll back to the Go code, and it'd be really confusing if a feature existed in the Go code and not the Rust code. And so we had to keep things one-to-one. And really, this came down to an idea of philosophy. We settled on the philosophy of a strict port, but it took time. And if we decided that early, then we probably would have spent like at least a cycle or two cleaning up the repo, writing more tests, and so on. Our testing story was pretty decent, but you can always write more tests. And especially when you're porting, you start to have to write tests that you wouldn't need with the initial version. If you load config in one way in the initial version, like you load your flags before your files, well, that's fine. That's just how it works. But when you're creating a second version, you suddenly have to worry about that, because what if your second version loads your files before your flags? You now have a bug, and you now have a breaking change. And so writing these tests beforehand would have made sure that we could have caught a lot of potential issues. And finally, we should have shipped nothing quickly. And what that means is, with each method, we should have shipped early and shipped basically an essential bare minimum version. Oftentimes, we invested in this porting method, and we ported a bunch of code, and then we tried to ship it, and that meant that there was a lot of pressure on. We basically had all this code that relied on this method, but if we couldn't ship it to users, then all that code would have gone to waste. And trust me, at times it seemed like we couldn't ship some things. So this is the wonderful PR that deletes all the Go code. It's, yes, you're reading that correctly, 72,000 lines deleted. I think it is the most satisfying PR I have ever merged in my life. So yeah, that was a fun one. And now that we're a few months out of the port, we've managed to build some really cool stuff on our new Rust foundation. The first really is that issues are way down. And in fact, this was kind of confusing. Like, we all had this conversation where we were like, there aren't issues coming in. And like, is something wrong? Like, we were like asking ourselves, like, maybe people are like, not able to submit issues, maybe like people stopped using it. But by all accounts, our metrics are going up and there are fewer issues. So I count that as a win. Next up is performance improvements. Now, we didn't actually get that much perf improvement from moving to Rust, because Turbo is essentially bound by I/O more than pure CPU. But we managed to eke out some performance improvements just by switching some things around post-Rust. We were able to leverage a daemon more. And finally, we shipped 2 new features, which are really cool. The first is better errors. We now print really beautiful errors with inline fixes, and we display the text of your config file. And to do this, we used Biome, which has an excellent JSON parser with line and column info. And we used Miette, which is an excellent error printing library that allows you to print errors in a really fancy way. The second feature is a new UI, which is really beautiful and gives you a better idea of your tasks. And we used an excellent Rust crate there called Ratatouille. So with that, I'd like to say thanks, and let me know if you have any questions. Yeah.
So you mentioned that you integrate or you call Go code from Rust. From top of your head, can you recommend, I don't know, library or blog post where this is described?
So I actually do have some blog posts written on the Vercel blog about this, so you can check those out. I will say that there isn't a good library for this, and this is the very nature of using an unconventional set of languages. Like, if we were porting from C++ to Rust, there would be a bunch of existing technologies to use. But really here, there was only like one blog post, and it involved writing assembly. And so we were like, I think we're good. I don't think we're going to do that route. Yeah.
How many lines of code you have in Rust version after port?
Yeah, sorry. The question, yeah, how many lines of Rust do we have? I don't know how many lines of Rust we have after the port. If I had to guess, it's probably more in some ways, due to just types and also just like new features and whatever. Also in Rust, behooves you to split things up into crates because you want to parallelize things at the crate level, so it, you just get faster compilation times. So, yeah. Cool. If that's it, then thanks.
What was the binary slice?
Sorry?
The binary slice?
Large, in a word. The binary size is quite large.
Between Go and Rust?
I can't tell you off the top of my head the difference between Go and Rust and the binary size, but
not significant.
not significant. And to be frank, that was not a concern of ours. Like, you know, yes, binary size is important, but also it's a native tool, so by its very nature, it's better than downloading, you know, half of NPM.
The experience of some of my friends was that they were coming from the JVM, so they were coming from, after porting from like, you know, hundreds of megabytes to like few.
Well, good for them.